Hi everyone, this is Harini. In this video, we'll be learning about how to implement doubly linked list using C. Doubly linked list. A doubly linked list is a linear data structure similar to a singly linked list, but here each node has an extra pointer that stores the address of the previous node corresponding to each node. Advantages of doubly linked list. It allows us to iterate in both directions. We can delete a node easily as we have the access to its previous node. Reversing is easy in a doubly linked list. Operations done on doubly linked list. We can create a node, we can insert a node, we can delete a node, we can delete a node at the end, we can delete a node at the beginning. To create a node, we use struct node. Generally, node is a structured data type. It contains two parts, data and address. In double linked list, node contains data, previous and next. This is the structure of node. Previous pointer points to the previous node and the next pointer points to the next node. So, in struct node, while creating, we define three variables. Struct node in data struct node previous pointer variable and struct next pointer variable. One pointer will be pointing to the other node. Let us take an example. If this is the created doubly linked list, this will be the head pointer. There will be nodes. Each will have two pointers. One will point to the next node and the another will be pointing to the previous node. This means that this pointer will contain the address of the next node and this pointer will be containing the address of the previous node. Head pointer will contain the address of the first node. As we can see here, we have the head pointer with its address as 100, which is nothing but the address of the first node. Tail pointer similarly will contain the address of the last node. Here for the tail pointer, we have the address of the last node. So in this, we have a pointer to the first node of the list and also to the last node of the list also. If we want to insert any node to the last without having the tail pointer, you have to traverse from the first till the last. If we have a tail pointer, in that case, you don't need to traverse the list till the end because directly we can insert one from the last by accessing the last node using pointer since we have the address of the last node in tail pointer. Tail pointer will take more memory space. Now, as we saw earlier, we have struct node in data, struct node of type previous, struct node next pointer variable. Since we have two pointer variables previous and next, we will be declaring two pointer variables. Struct node head, a temporary pointer variable called new node and a tail pointer variable. We are defining a new function called void create. The data type of the node is struct and head will store address of the first node. Similarly for tail will store address of the last node. So we are declaring them like this. We will now create a new function called void create. This will be used for creating the node. We are declaring a pointer variable using struct data type. Struct node star new node equal to size of struct node. We are using the malloc function. This is used for dynamic memory allocation and it provides the size for a node. The size of function is used to give the size of the node for the memory allocation. The address of this will be stored in new node pointer. After executing this statement, memory has been allocated for that particular node. Let this be a newly created node. New node will be a pointer that is going to contain the address of newly created node. malloc will return this address 100. This address will be stored in new node. Hence, new node pointer is pointing towards the node that is containing address as 100. Let us assume head to be null, which means we don't have anything in this list. We have to insert data to the node, for which we use scanf function. Scanf %d, comma, ampersand, new node of data. Data can be accessed only by using pointer. That pointer variable should be pointing to the node. We can clearly see that new node pointer variable is directly pointing to the node created. So we use ampersand new node of data. To access previous node, we use new node of previous equal to null. And similarly, to access the next node, we use new node equal to next equal to null. How to insert this node to head pointer? Head will now store 100, which means head will point to the node. Since we are maintaining this tail pointer, in tail we are storing 100. So in this case, we can clearly see that head equal to tail equal to 100. From where will we get 100? Address of the node is stored in the pointer variable called new node. Hence we write head equal to tail equal to new node. This is in the case if head is equal to 0, that is if the list is empty as we saw in the previous case. If suppose we want to add another node and that node has an address 200, then the new node pointer variable will contain 200 and in that case we repeat head equal to tail equal to 200, then head and tail will point to the next node that is containing address equal to 200, thereby losing the reference to the first node containing address equal to 100. So this should not be a case and this should not happen. For this, we are using a condition. If head equal to null, then we are declaring head equal to tail equal to new node. If head equal to null, then head equal to tail equal to new node. But now, if I want to insert second node with address equal to 200 and new node to 200 because of that, from the user input, if the data inserted is 6 and previous and next has null, here you will be storing address of previous node, that is 100, and here you will store address of next node, that is 200. Then a link will be established. As we can see here clearly, you will be storing the address of previous node as 100 and the address of the next node as 200. Eventually, the new node will be containing 100 and 200 respectively for both the nodes. And so, now null value will become 200 and will store the address of the next node, and in the second node the previous value will be 100, thereby storing the address of the previous node. Now tail will be pointing to the last because this is the last node, so the tail will be storing 200. We are changing the 100 to 200 now. So, if head is not null, we will go to the else part. As we saw earlier, tail will be pointing to the next equal to new node. This is the else part. Tail will be pointing to the next node equal to new node. New node will be pointing to the previous node equal to tail, and tail will be equal to new node. Hence now tail will point to the next node. Let us look at a case where we have to insert a node at the beginning. Let us take a case. We have these three nodes in a doubly linked list with head as 150, tail as 200, and address of each as 150, 100 and 200 respectively. Now we should insert a node at the beginning of the list. Let us consider this node to be inserted at the beginning of the list. The node to be inserted has a new node of value 500 and the node's address is 500. We are defining a new function called void insert at beginning. Struct node. We are declaring a pointer variable new node. The code follows the same as in create, but the only difference is that we will be updating this pointer, and so we will not be writing new node next equal to null as written in create. The node to be updated is this one, the next pointer node of this node. Since this is to be changed, we won't be using new node of next equal to null. Let us assume the list is not empty. If we have to insert this node to the list, second node's previous pointer will be containing the address of the first node. We can access this part by using head, since pointer to this node is connected to head. The address of this node is 150 and the head value is 150. So this is connected to this node. The new node's value is 500 and the address of this node is 500. To connect and link these two nodes, the address of them must be same. That is, address of this node should be equal to value of the previous node. Hence, we are changing this null to 500, thereby linking this to this one. This will be pointing to this node. Again, we are changing null to 150 for this node to point to this node. Thus, a link is established between both the nodes. This node should point to this node whose address is 150. So the next pointer variable of the node to be inserted should contain the address of the other node, that is 150. How to access this pointer variable? We can access this pointer variable by using new node of next equal to head. In the previous case, we used head of previous equal to node. We will be implementing the same in the code. As we said earlier, we have made the necessary changes. Head of previous equal to new node and new node of next will be equal to head. Now head value will become 500. Similarly, we will be doing the insert at the end. For this, we will be declaring a function called void insert at end. We will be using the same code, still getting the data. But in this case, we will be using tail pointer to insert at the end. The new node will be containing the address of this node and tail will also contain the address of this node. So, tail will be pointing to this node, new node will be pointing to this. Establish connection between both the nodes. This pointer will be containing the address of the next node and the other pointer will contain the address of the previous node. This is how link will be established between both the nodes. That is, null will be changed to 400 and null in the other node will be changed to 200, thereby establishing a link between the two. This node will point towards the other node and this pointer variable will point towards this node. So tail of next will be equal to new of node. New node of previous will be equal to tail, thereby tail will be equal to new node. Deletion from a doubly linked list. For deletion, we will be using free function. Deletion will be done using tail as the main key. For deletion, we will be using the following function. We will be declaring a new function called void delete from beginning. Struct node temp. We will be declaring a new pointer variable called temp. If head equal to null, then print the list is empty. We already know that if head equal to null, then the list will always be empty. In the else part, we will be writing temp equal to head. We are assigning temp equal to head. Value of temp is 200 and value of head is 200, as we can clearly see here. Then head equal to head of next and head equal to head of previous equal to null. Thereby these links will be broken, and by following this code we will be typing and making the following changes. 400 will be changed to 0 and 200 will be changed to 0, thereby breaking the link between the two nodes. Thus links will be broken, then memory alone will be present. To free up the memory, we will use free function. So now to free the memory, we use free of temp. Now the memory too will be deleted, and hence the node along with the memory will be deleted. This is how we delete from the beginning. Similarly, same thing will happen if we delete from the end. For this operation, we will be using a new function called void delete from end. We will be copying the same again and creating a temp variable. The condition changes in this case at the end. If tail equal to 0, since we are coming from the last, we are using tail variable here. As we can see, we are deleting at the end, and so tail variable will be assigned as null. In such case, list is empty. In the else part, we will be writing the following code. Temp will be assigned as tail, and both will be having the same value as we can see here. So as we can see here, temp will be containing the same value as that of tail, and then tail of previous we are declaring this variable this to access the node to be broken using this line. So previous of Next will be equal to null. Tail equal to tail of previous. Now free temp. Memory 2 will be deleted. This is how we delete node from the end. By following the same code, we'll be making the following changes in this too. So this node 150 will be changed to 400, thereby copying the address of the node. So tail variable will be pointing to this node. Now we will be making this to null value 0, and then we will be breaking the link between the two, thereby deleting the node at the end. This is how node is deleted from the end. The time complexity of doubly linked list varies for both insertion operation as well as for deletion operation. For insertion operation, the time complexity will be 0 of 1 or 0 of n. For deletion operation, it will be 0 of 1. Doubly linked list applications. Redo and undo functionality in software, forward and backward navigation in browsers, and for navigation systems where forward and backward navigation is required. This is all about doubly linked list. Thanks for watching.